All right. Welcome everyone. Today we're gonna do a new topic. We're gonna do still ACS exam preparation, but we have kind of like a new topic over here. So the previous one we are talking much about uh aqueous reaction and solution, right? But today we're gonna discuss especially particularly in the topic chapter 6. If you are like looking at your textbook, it will be in the chapter 6, and then we are discussing heat and enthalpy. Okay, so let's get started, guys. How to solve the problem one by one. All right, so number one. Okay, what is the energy change for a system that release 100 kilojoule of heat to its surrounding and has 25 kilojoule of work done it? Okay, so what is the energy change for a system that release 100 kilojoule of heat to its surroundings and has 25 kilojoule of work done on it? All right. So, how to solve this problem? How to solve this problem? The key concept of this problem, the main idea here is the first law uh, of thermodynamics. Okay, thermodynamics. Okay, which says, okay, the change in internal energy of system, okay, the change in internal energy system equals the heat exchange plus the work done. Okay, so it tell us what the total of energy, okay, the change in energy internal energy of system, which is delta E, equals the heat exchange, okay, plus work done. Okay, work done. Okay, so now let's move on to more detail to solve the problem. Okay, to solve the problem. But watch the signs first before going through solve the problem. Okay, if heat release, okay, this is the key. If heat release, okay, heat release, so the sign it will be negative, or Q will be negative. Okay, if heat it if well, let me like the same, if heat gaining, it Q will be positive. Okay, however, if work is done on the system, okay, if work done on the system, in system, W is positive. Ini W will positive. Oh, ganti nak ganti. Maaf, maaf. Jangan. Okay, sorry guys. So if work is done on the system, remember on the system, the W will be positive. Okay, W will be positive. So now solve this problem step by step. Okay, so let's fill in the numbers. Let's plug in the numbers. Okay, heat, okay, the system release, okay, the system release, which tell us release 100 kilojoule, which says Q, okay, will be negative, okay, release. And then how about the work done on it? Has 25 kilojoule. 25 kilojoule work is done on the system, which tell us W will be positive. All right. So now just plug into the formula. Plug into the formula which tell us delta E or energy, internal energy, is Q plus W. Q, what we have here is minus 100 and then plus 25 kilojoule. So the answer will be 75 kilojoule. Okay? So yeah, the system lost more energy as heat that it gains as work. Okay? The system lost more energy since, okay, it gains as work, so the total energy change is negative. Okay, so when you see heat release, always use negative. Okay, when use remember, okay, remember when you see the heat, okay, if heat release, always use a negative sign for Q. And if work is done on the system, W will be positive. Remember, okay? Just watch the sign. Okay, this is for the first question. And then use this number. And then remember, if heat release, Q will be negative. Okay, remember, double E, Q plus W. Q plus W. Energy internal, okay? Internal energy equals the heat exchange, okay, plus the work done, okay, the work done. All right, so remember this part. And then remember again, if heat release with which is saying about Q being negative, okay, Q or heat will be negative. And then if work is done on it, I mean on the system, it will give us work in positive. Okay, and then based on this information, the system lost more energy. Okay, the system lost more energy because of what? Because heat release. Okay, heat release more than work. So the total energy change is negative. All right, so number 2. 1 gram sample of carbon and copper originally at room temperature reach equilibrium after being placed in 200 milliliter of boiling water. Which statement is correct? Okay, which statement is correct? Now we need to solve this problem. Solve this problem. I mean, we need to get more detailed information over here. Okay. Now, first things first, we have information about was that the volume. We also have information about specific heat. Okay. We have information about specific heat, about the volume. And then the concept is, okay, the concept is, the important idea is specific heat capacity. Okay, that's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Kelvin or Celsius. I just want to restate again. Specific heat capacity, that's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Kelvin or Celsius. Repeat it again. The specific heat capacity is the amount of heat required to raise temperature, okay, to raise the temperature of 1 gram by 1 gram of substance by 1 degree Kelvin or Celsius. Okay, this is the most important concept. Okay, higher, which mean higher specific heat, the substance is more resistant. Okay, kind of like carbon. Okay, higher, so higher will be more higher, which mean what? More resistant. More resistant. Okay, to more resistant to temperature change. Temperature change. Okay, it takes more energy to heat it up. Okay, like I mentioned, because carbon specific heat capacity is higher, like it needs, like it's more resistant to temperature change. Okay, it more resistant to temperature change. It takes more energy to heat it up. Okay, when both sample reach equilibrium, okay, the second concept is when both sample reach equilibrium in boiling water, they will put ended up at the same final temperature. Both are ended up, right? They will put ended up at the same final temperature. Okay, now let's break it down one by one. Okay, okay. Uh, let's think this through. Okay, let's think this through. What sample have the same mass? The 1 gram. Okay, both samples have the same mass. Okay, and reach the temperature. Okay, reach the same final temperature because they are in the same boiling water. But, however, specific heats are different. Okay? So, based on this information, guys, okay, I will explain, like re-explain again. Both samples have what? Same amount or same mass. Okay? Same amount or the same mass. And reach the same final temperature. Okay, let's, as you can see, reach equilibrium after being placed in boiling water, and then they both reach the same final temperature. However, their specific heats are different. So carbon should be takes more energy rather than copper, okay, to raise its temperature. Okay, copper needs less energy for the same temperature change. Okay, so for equal mass and equal temperature change, it will be Q mc delta T. Okay, with the same mass, if we take a look at this part, if we have the same mass, we can cancel out. Okay, and then we also have the same temperature. We can cancel out as well for delta T because the both have same temperature, the same temperature. Okay, both have the same temperature change. The difference is C itself. Okay, heat capacity. Heat capacity. So which statement that correct? Okay, with the same M and T, the higher carbon absorb more heat. Okay, higher C absorb more heat. Lower copper absorb, lower C absorb less heat. Okay, now let's take a look at the option. Copper will absorb the same amount. No, no. Okay, no, not the same amount. B. Copper will absorb the same amount of energy as carbon. Nope, right? Because like I mentioned, Cooper, uh, uh, does Cooper has same specific heat? No. Okay. And then again, guys, again, over here. Let's take a look at this one again. Okay, let me change this part. Let me change the ratio. I thought that it should be give much more space in the bottom. That is great. Okay, now it's great. Okay, so Cooper will so because it still says the same amount, so the answer will be not this one. How about the C option? Cooper will absorb less energy. Yes. Okay, less energy than carbon and attain the same final temperature as carbon. Let me think. For C, yes, it should be yes, right? Cooper absorb less energy to attain the same final temperature because, like I mentioned, if the specific heat capacity lower, it will raise temperature easier. And then because what? Because like I mentioned before, because uh specific heat means the substance is more higher, like lower specific heat capacity, it will be easier, like less resistant to temperature change. Okay, less resistant to temperature change. And then how about D? Cooper will absorb more energy than carbon. Okay, this statement is opposite. Okay, no, it's opposite, so the answer will be C. So just quick recap, guys. When the final temperature is same, okay, is the same, the material will with the lower specific heat absorb less energy. Okay, all right. So let's move on to another part. Okay, let's move on to another question for the next question. Just remember, you guys. Uh, remember equation about first law of thermodynamic. It tell us like internal energy, which is delta E equals Q plus W. If heat release, Q will be negative. Okay, if Q positive, which means it will gain heat more. Okay, and then W it telling us about uh, if work done on the system, it will be positive. If work done by outside the system, it will be negative. Okay, so let's take a look at another question. And remember as well for this equation that I showing you guys, that I show you. Now, move on to another question. So before I'm going to discuss for next question, let me take a break for a while. Hmm? Really care? All right. I'm so sorry because I'm a little bit cold. So yeah. So I need to take a something, and then yeah, let's continue our discussion, guys. So now we move on to another question. This question is telling us about calorimetry and specific heat. Okay, this question is telling us about calorimetric and specific heat. Okay, so 10 gram of silver is heated to 100 Celsius and then added to 20 gram of water at 23 in insulate calorimeter. After mixing, the final temperature is 25 degrees Celsius. What is the specific heat of silver? Okay, so this is the calorimetric problem. Okay, this is the calorimetric problem. Calorimetric problem. So how to solve this one? The heat loss, okay, equal, okay, will be equal heat gain, by water. So you have 10 gram of silver and then you heat it to 100 degrees Celsius and then add it to 20 gram of water at 23 degrees Celsius in insulate calorimeter. A thermal equilibrium. The temperature if the system was measured as 25 degrees Celsius. So, as you can see over here, guys, since the container is insulate, we can use the formula is Q MC delta T. Okay, so I think like all of type question in the ACS exam, it will be insulate problem, not like an insulate container, because if we are dealing with the uninsulate or like open system, something like that, it will be much more complicated. Okay, it will be much more complicated, but hopefully we didn't, I mean, we do not getting any kind of like this problem. I mean, for open system, this is the closed system, right? QMC delta T. Let's set it up first by first, step by step. Okay, first step is silver. As you know, silver, okay, we need to determine the mass first. Okay, mass is 10 gram. How about the C of what? C of silver. Okay, C of silver. So but however, we need to know, okay, we need to know the C itself. Okay, what is the specific heat of silver? We need to know the C itself. Okay, and then we have delta T. Okay, as you can see, guys, the delta T, the first temperature, uh so the temperature itself for from the beginning is 20, it's cooled down, right? It cooled down. Okay, so the first one is 25. Okay, 25 minus 100. Okay, 25 minus 100. Okay, so it will be 75. And then how about water? This one is for silver. Okay, how about water? Water mass is 20. Okay, M is 20. And then specific heat over here is already have specific heat 4.184, and then initial temperature is 23, right? This one. And then it heated up becoming 25. Okay, so it will be was that it will be uh oh no, uh so it will, wait, C is 4, okay, and then for delta T is 25, right, minus 23, so it will be 2 degrees Celsius. All right, so let's move on to another equation. So like I mentioned, guys, heat loss will be same with heat gain. Okay, heat loss, it will be same with heat gain. So as you can see, M1 C1 delta T, okay, so it will be plus, right? So first of all, heat loss, okay, will be heat gain. So for initially the was that the equation will be like this one, MC delta T. Okay, and this is 2 because we want to put in over here, right, heat gain. So heat gain, this is minus, right, heat loss equal minus heat gain by H2O. So we put it over here, M1 C1 delta T plus M2 C2 delta T equal 0. Okay, so now we just put in the equation. We just plug our number. So M is what? 10. C, this is the thing that we want to know. And then delta T is minus 75. Okay, minus 75. Okay, because it's cooling it down. Okay. Okay. Wait. All right. So now let's plug another one. Plus what is M2 is 20. 4.1 equals 4, delta T is 2. So now we will get for C itself. Okay, so this is 0, right? This is 0. So solve one by one, it will getting like minus 7, this one, C, right? And then plus what this one, 167.36 0. So it will give us for C is it will give us kind of like 167.36 divided by 20 minus 750. So it will be minus as well, and then so it will give us number is 0.223 joule per gram Celsius. Okay, so just round it, this one, it will be 0.22. So the answer will be P. Okay, the answer should be P for this question. All right, that's true. The answer P. Okay, now let's move on to another part. Just remember, if we getting the question kind of like this one, please use this concept. Okay, use the calorimetry concept. So you will be given by like silver and then water and then something like that, and then you put in together, right? And then you will use the heat loss equal heat gain. Okay, now let's move on to another question. Okay, let's move on to another question. What mass is needed to release 45.2 kilojoule of energy as heat during reaction carbon and chlorine gas? Okay, what mass of Cl2 gram is needed? Okay, in gram is needed to release blah 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 blah. Okay, how to solve this problem? Still same. This is the heat enthalpy or stoichiometry and enthalpy. Okay, the key idea over here is the enthalpy change okay, is the enthalpy change is per mole of reaction. Okay, as written. For every 2 mole, for every 2 moles, okay, of Cl, it will be 135.4. Okay, as you can see over here, this is the reaction itself. Okay, so for every 2 mole Cl2 minus 135.4 are released. Okay, minus, which mean release. Okay, what mass of Cl2 is needed to release blah 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 as heat during the reaction of carbon and chlorine gas. Okay, now we, if based on this information, guys, see this one. Okay, as you can see, delta H over here is minus 35 are released 2 moles. Okay, released to 2 moles. How many moles of Cl2 are needed to release this one? Okay, if use if using this kind of the data, we release this one, 2 mole release minus 35.4. okay, and then now we need to know if we just want to release 45.2 kilojoule. Okay, so how to do that is pretty easy, just using the calculation. Minus 45.2, okay, because it's released, right, kilojoule, times 2. Okay, let me bring you some something that more logic. If 2 adds to Cl, 2Cl, okay, or 2 mole Cl, it will release 135.4. Okay, 2Cl, which means 2, right? How about if we want to release 45.2? Over here is x. We can ignore for the sign first. Okay, so based on this information, we will get information x 135.4 equal 45.2 times 2. 45.2 times 2 divided by 135.4. The answer would be 0.667. So the answer would be A. Okay, so it's pretty easy, right, to solve this problem as long as we understand what kind of what they are, what they ask, what the problem is. This is the issue, because sometimes we don't know like how to solve the problem because we don't know what's the meaning of the question. Okay, what's the meaning of question? Okay, don't worry, guys, don't worry, because we want to practice more when we are doing for the was that the the practice question, okay, for the real practice question. Not this one is just study question, so it's kind of like a little bit much more detailed because of we want to know more about the concept over here. Okay, later on it might be much more easier for us. Okay, now move on to another part. What mass of benzene must be burned in a bomb calorimeter to raise its temperature by 15 degrees Celsius. What mass of benzene must be burned in a bomb calorimeter? Okay, it's kind of like same the previous one, as long as you understand about the equation like Q mc delta T. Okay, delta T itself is 15, right? And then calorimetric constant is 1.259, and then this one is 41.9. Okay, 41.9. Yeah, just do calculation for that one. Okay, 41.9 divided by 250, no, 1.2059 times 15. So mass, it will be 2.21 or 2.2. So very easy for this one, right? Very easy. So just remember the equation mc delta T. Okay, remember mc delta T. All right. So now we want to go through another question, right? Okay, just kind of like remember for key mc delta T that we already done. Okay. Okay. But however, guys, however, this is like just need to just simplify the problem. However, when we want to understand about bomb calorimeter, the original equation is QC delta T. Okay, QC delta T. Heat absorb, C calorimeter constant, and then others thing. Okay, so C still same thing, not much different. Let me. So what's the answer? 0.50. Oh. So the answer is incorrect, guys. Not this one. Okay. So the answer, what's mass of benzene? Oh, yes. Okay, I'm so sorry, guys. I got wrong over here. Okay. So, how to solve this problem? I repeat it again. Okay, this is the calorimetry and stoichiometry question. The idea is the heat release by burning benzene will be absorbed by calorimeter. Okay, when you heat it up benzene by burning it, okay, it will be absorbed by calorimeter, raising its temperature. Okay, so the formula is kind of like this. Okay, so for the first step, calculate heat needed to raise temperature. So using this equation QC delta T, we will get 18.885 kilojoule. So to heat it up 1 degree Celsius, okay, to heat it up to raise the temperature till 15, it needs 18.88 kilojoule for the Q. Okay, now we need to take a look at relate Q to the mass of benzene. Okay, delta HV combustion, okay, will be minus for from this information 41.9 kilojoule per gram. Okay, so now it's negative because it's exothermic heat release. Exothermic. Okay, so now we want to use the equation of the equation. Okay, so what's the equation is delta HF, okay, absolute delta HF times m q. Okay, we will get the q if we will get the m if we use if m equal q over hf. So it will be 18.885 kilojoule. HF itself is minus 41.9. So it will getting we will get added up like 0.459 gram. So it will be, the answer will be A. That's it. Okay. Just recap. Always use QC delta T. QC delta T if we want to use bomb calorimeter. Okay, bomb calorimeter. QC delta T if we use the bomb calorimeter. And then use the absolute value of delta H combustion to solve for mass, which is using this equation. Okay, which is using this equation. Keep your after that we done. Okay, after that we done. Just remember this equation. Okay. All right. Now move on to another part. Now standard enthalpy of formation for HF. Okay, what is the HF for standard enthalpy for HF in gram? Okay, as you can see guys, the choice over here is just kind of like which one that representing this balance. Okay, the equation balance equation over here. Okay, so the key concept is standard enthalpy of formation delta HF. Okay, delta HF is for 1 mole of compound. Okay, 1 mole of compound formed from its element in their standard range. Okay, standard states. Okay, so for each 1 mole of compound formed from its element in their standard rate state, sorry. So let's take a look at this reaction. 2HF, okay, G, and then becoming H2 and then F2. Okay, now let's take a look at the solution one by one. Okay, so now 2HF, this is the reverse formation. Okay, this is the reverse formation. So the standard one, the formation, it will be H2 and then F2 and then 2HF. This one is the formation. However, in this reaction, it reverse. Okay, this is the reverse formation. Okay, and for 2 moles, so the reverse reaction will be the reverse reaction will be H2F2 and then 2HF. And then now we need to change of the sign because we like put in opposite sign. Okay, so this is the original one. Okay, this is the original HF. However, let me show you. This one is reaction. Okay, and then this one is the original reaction. We want to know the delta HF, which means HF is formation. Okay, there is a HF formation and there is a combustion and other stuff. Okay, for formation, this is the original one. Okay, delta half H2 or half F2 and then becoming HF. And then if we need to give if we want to get 2 mole, the delta formation will be something like that. Okay, something like this. So to align with this reaction, we need to put in this sign minus, okay, minus delta H air reaction RXN. Okay, so let's take a look at the option. Okay, the option is the good answer will be B. Okay, because we want to what? We want to let me uh so the question is about what? The question is okay. So for HF, what we want to know is just one HF. This one is 2HF. 2HF is delta H, R, and X. How to get the just half? It's just put in half over here, H and S. So the answer will be P. Yeah, that's true. If we use this one, okay, if we use this one, the question should be what is the delta HF for 2HF? Okay, for 2HF. Okay. How about the C? The C is wrong sign. Okay, wrong sign. And then D, wrong direction and amount. Okay, so not correct. Okay, so the correct answer is B. Okay. All right. So just remember delta HF is formation. There is also delta combustion, right? So we understand now like much more detail of the type of equation. Okay, now let's move on to another equation. So given this equation, okay, given this equation, and then use the information to calculate the enthalpy of formation. So the product should be SO3. Okay, the product should be SO3. So it's pretty easy to solve this problem. Just SO2 in gram becoming S in solid and then O2 in gas, right? And then we want to get the SO3 as product. Okay, to SO3 as a product. This is the what we want to get. Okay, this is what we want to get. However, guys, it's two. Okay, it's two. What we want to see is just one. Okay, just one. And then this one is delta H1, and then this one delta H2. Okay, so how to solve this problem? Firstly, we want to make it SO2, not 2SO3. Okay, we want to make SO3, not 2SO3. How to do that? Just divide it by half. Okay, so it will be 2SO3 plus O2. SO3 plus O2, right? O2. This is in what's the type? This is on in gas, right? This is SO2, sorry, plus O2. No, sorry. So it will be SO2, sorry, this is should be SO2, right? Plus half oxygen plus SO3 in gas. So what we want to see in the product, it should be this one. Now we need to cancel out the reactant. How to do that? Okay, how to do that is not probably the simple way is just reverse it. S in the this as solid and then O2. So what I want to do here is okay, what I want to do is over here is just put in S and then plus O2 and then SO2, which is it will be, I mean, it give us minus delta H1. Okay, this one is half delta H2. Now try to kind of like cancel out one by one. This one cancel out with this one. Okay, so now let's combine both. So S plus half O 3 half O 3 over 2, and then it will be SO3 in gram. So how to get this one done is pretty easy. Uh just using minus delta H1 plus, right, half delta H2. So the answer will be what? Will be B. Okay, the answer will be B. Yeah, the answer will be B. Okay, just use like kind of like using the simple way to solve this problem. Just using this, just visualize the like math. Okay, like math. We need to cancel out this one and this one, and then we ended up getting the answer. Okay, now move on to another part. Given this thermochemical data, what is the delta H reaction for this one? Okay, so now, okay, for this one, right, for CO2 plus half O2 and then CO2 in K, sorry. So now let's take a look at this one first. Okay, let's take a look at this one first. Now we can do something similar like before. So what we want to do here is like C, okay, CO2 will be product, right? So we put in C plus O2, CO2, and then this one is 394 minus, right? And then for others is I just want to put in reverse, so it will be to CO and then becoming to C and then plus O2, and then I wanted to half, okay, divided by half, so it will be 1, right, and then it will be 1, and then it will be half for this one. Okay, it will be half for this one. Okay, good. Now try to cancel out one by one. Okay, this one will be cancelled out with this one will be cancelled out this one, but still half O2. So however, this part, it will be minus 2021 divided by 2. But however, the sign over here, it will be plus. Okay, it will be plus. So now we just want to put in over here CO and then put in half O2 and then now CO2 and then minus 34 and then let me think, 2 to 1, right? 2 to 1 divided by 2, it will be 110.5. Okay, so the answer will be minus 288.5. So the answer will be P for the last part of the studies. The answer of this one, it will be P. Yeah, probably, I don't know. Let me check for the key question, the key answer to study question. This is number A. Yeah, it should be P. Yes, that's true. That's true. The answer P. Yeah, the answer P. Yeah, that's good. So the answer is P. Now let's move on to another part again. Okay, let's move on to another part again. Okay, just like recap for the previous question is when using Hess law, reverse equation reverse equation, change the sign of delta H. Okay, if you look at the equation, okay, and then it will be matching up if we do reversing. So just reverse equation. However, remember to change the sign. Okay, and then to multiply or divide, do the same with delta H. Okay, if we do the if we want to do dividing, okay, or multiplication, okay, so multiplication, we do multiply with delta H. And then if we do add reaction, we need also to add their delta H values. Then carefully cancel species to match the target reaction. This is the key. Okay, now we want to do the last question of the studies question, and then after that we're gonna move to real question. Use the enthalpies of formation delta HF in the table to determine delta H for this reaction. Okay, let's take a look at. We have two CH2H2. Okay, so it will be 227 times 2. Okay, and then we do not count for O2 is okay. And then how about the CO2? CO2 is 4, so it will be 4 times minus 39.3. How about the 2H2? 2H2O, it will be 2 times minus 24.2. So how to do that is very easy. Just using delta H reaction, okay, delta H reaction using the standard enthalpy of reaction, okay, product, okay, delta H product minus delta H reactant, okay, reactants. Okay, from this information, guys, we just plug this information to this one. Okay, so sum like 4 times minus 393 plus 2 times minus 242, right? And then minus again 2 times 227. Okay, so based on this information, we will get thing just do math so every step, right? And then the total product is this one is minus 1572, and then minus again 484. Okay, and then the last step is just count the overall. The total of our reactant is minus 25056 kilojoule. However, the question is, okay, delta H for this reaction. Okay, so the react, okay, oh no, wait, I do something wrong. 4 times 393, it will be, oops, sorry, minus 1572 minus what again? 242 times 2 minus 484 minus again 2 minus 227, 2 times 227. Oh god, minus 1572 minus 484 minus again 2 times 227. So the answer will be 2510 minus 2 times 227 minus 445. So the answer will be this one, 2510. So the answer will be D. Just remember the equation, the product minus reactant. Okay, this one. Okay, so the answer will be D. Oh, sorry, will be A. Sorry, guys. Sorry, because we need to remember the sign itself. The sign is minus. Okay, not D. D is plus. Okay. So use product minus reactant for enthalpy reaction. Remember delta H for any element is standard like O2 is 0. Okay. Multiply each delta HF by its coefficient in the balance equation. Okay, and then it's done after that. Okay, so let's finish for this one first, and then I wanna continue for the next part in the another session.